And good evening, AP Physics students. Mr. Curson coming at you here. We're going to talk about capacitors today a little bit. All right. So we're going to talk about in Chapter 17, Problem 42. Okay. Now, we might be wondering to start out, what in the world is a capacitor? Well, a capacitor, and again, Mr. Curson likes nice, short, simple definitions we can remember, not official or anything, but a capacitor is a charge storage device, so something that stores a bunch of electrical charge. Now, of course, as you're storing charge, you're also storing energy. Now, you might say, Mr. Curson, isn't that a battery? Well, they're different, and we're going to talk about why. The simplest type of capacitor is called a parallel plate capacitor, and as you may guess, it's two parallel conducting plates separated by air hooked up to a battery. And what happens is charge flows on to the positive plate from the positive terminal, and negative charge flows on down here. So we get charge plus Q down here and minus Q down here. And then there's air in between. Now, the simplest example I can think of as a capacitor is, I don't know if you've ever had a disposable camera, but you press the button on the disposable camera to charge up the flash, right? And you hear the little wing, right? You're charging a capacitor, and then boom, you hook that capacitor right through the flash, and you get a bunch of charge, a bunch of energy that comes out as light released all at once, all right? So, this is a parallel plate capacitor. It's the most simplest type of capacitor. Now, the capacitance of a capacitor is defined to be the amount of charge the capacitor can hold per unit charge. Okay? So, if I had a 1 volt battery here, and that 1 volt battery was able to put 1 coulomb of positive charge on the top plate, and 1 coulomb of negative charge on the bottom plate with only 1 volt, we would call that a 1 farad capacitor. So the SI unit of capacitance is defined to be the farad, which is abbreviated with an F. Of course, this is named after Michael Faraday, who invented a whole bunch of things in electricity and magnetism. So, another name for a farad, 1 farad, is 1 coulomb per 1 volt. Okay? So, now, 1 farad is an awfully large amount of charge. A lot of times we talk about microfarads or picofarads, 10 to the minus 12, small things like that. So this is a formula for a capacitor in general. Well, Mr. Kirsten, if this, was 1 meter, with this plate here, if this conductor had an area of 1 meter squared and they were 1 meter apart, how much capacitance would this object actually have? So you can physically find out just from measuring the capacitance of a substance with the following formula. The capacitance of a parallel plate capacitor is equal to a constant times the area of the plates divided by the distance. So this metal plate, I'm kind of drawing this like as a head-on view, right? This metal plate would probably extend back like this and have some area, right? And this plate down here would have some area also. And then, of course, D would be the distance between those two plates. Notice as the area gets bigger, the capacitance would get larger. So the bigger your capacitor, the more the charge can spread out, and the more charge you can have that on there. That makes sense. And the smaller the distance between the plates, all right, so the smaller this gets, the larger the capacitance. All right, I should probably tell you what this constant is, epsilon naught. This is called the permittivity of free space, and it is equal to 8.85 times 10 to the minus 12 newtons times coulombs squared per meter squared. You may have seen this before. our constant k, 9 times 10 to the ninth, is 1 over 4 pi epsilon naught. Okay? Now don't forget these constants, k, epsilon naught, I should probably write epsilon naught is the permittivity of free space. All of these constants are on your table of information. So don't forget to have that handy for quizzes and homework quizzes and all that kind of stuff, because it comes in handy with all of these constants. All right, we've got one more thing to talk about before we dive into this problem. And once we dive into the problem should go pretty quick. So it's inconvenient many times to just have two parallel plates with air in between them. What's really nice is if you can take your object, your capacitor, all right, and take your two plates and put actually something solid in between them, something solid that doesn't conduct electricity. This is convenient because then you could take your parallel plates and you could do something like this, where you roll it all up together and keep it in one nice little unit. Here are some actual capacitors, and I'll show you some in class also. Now, not only does this keep the two plates from touching each other, but you can actually increase the capacitance of your capacitor by a factor K. And this K for different materials is called the dielectric constant. Okay? So if we want to add into this formula down here, we could add a little constant K based upon the material you're using. Now, here's just a little chart of some different dielectrics. Air has a dielectric of 1, paraffin wax 2.2, etc., etc. All right. So if we put a solid in between here, we're most likely going to increase the capacitance of our capacitor. Okay, on to problem number 42 here. All right. Problem 42 states I have a capacitor and it is filled with the dielectric paraffin wax. And it's a parallel plate capacitor. And the distance between the two plates in the parallel plate capacitor is 1.8 millimeters. The square plates on top are 5.5 centimeters on each side. And we want to know what is the capacitance of this capacitor made out of paraffin wax, two square plates, and a certain distance apart. Well, this is right up the alley of the equation we just talked about for the capacitance of a parallel plate capacitor with a dielectric in it. So the dielectric constant here, I'm going to look up for paraffin wax. Looks like that's about 2.2. All right. So by having that in there, I'm increasing the capacitance by that factor. We've got our permittivity of free space, 8.85 times 10 to the minus 12. We've got our area. So area would just be the length of one of the squares squared, right? So 5.5 centimeters is 0.055 meters. Square that. And divide that by the distance between the two. So that'd be 1.8 times 10 to the minus third, because we want to put everything in meters so everything works out nice. So if we plug in all those numbers, I get 3.3 times 10 to the minus 11th farads is the capacitance of this parallel plate capacitor. So in other words, if I put a voltage of 1 volt across the plates of this capacitor, I would get 3.3 times 10 to the minus 11th coulombs worth of charge on each plate. All right, nice job, AP Physics students. For your funny thing today, we are going to do something kind of special here. Here, I am going to put a snossage, a dog treat, on here, and we're going to see if something interesting might happen to the snossage here. Oh, Raven, you got a snossage. All right. Nice work, physicists. We'll see ya.